Good afternoon, everyone. Can you all hear me? Okay, great. Okay, so I'm looking at the calendar here. It looks like we're going to have exam 1 the week after next. So I want to be able to have I guess it would be the 4th quiz before the exams. This would put us to Wednesday, the 24th. February 24th for the first exam. So that'll cover the interfacing material, the control systems material, and hopefully I'll get through real-time scheduling by then too. I think I will. So it'll be on those 3 topics. We have quiz number 3 rather is already out, and it will go live at 5:10 after class today, and it will be due next Monday at 3:55 before class, just like I did quiz 2. That seemed to work out pretty well. So quiz 3, which will be on control theory, will open up after class and will be due a week from now before class. So I'm going to start out. I'd like to go over quiz 2 briefly. I'll go through it really fast though, just to make sure there aren't any questions. I looked at the grades and everyone did very well for the most part, so I'm just going to run through it real fast. Okay. Okay, so hopefully you can see my window. Yes, okay. Okay, great. Okay, number 1, how many bits are sent in each direction in an SPI exchange? That's 8 for an SPI transaction consisting of a write. How many bytes are sent from slave to master? So this one is a little tricky because you're doing a write, which means that the master has to send 2 exchanges or 2 bytes to the slave, but the slave doesn't have to send anything back to the master. So the answer is 0 there. For a multi-SPI, and by the way, if you guys have any questions about any of these, let me just post them in the chat. For a multi-slave SPI channel that has 1 slave select signal for each slave, how many slaves can transmit at any given time? 1, because they all have to share the 1 MISO wire. MISO, that's the wire from the slave to the master. So because they're all sharing 1 wire, only one of them can drive that wire at one time. What's the result of 2 devices sharing a single wire? What is the result of 2 devices driving a single wire to logic 1 in a push-pull driver? Well, I mean, if they're both driving to logic 1, then the wire will be logic 1. So the problem with push-pull drivers is when you have 2 devices driving the same wire, but they're trying to pull it in opposite directions. One pulling it to 0 and the other pulling it to 1. And if that were the case, then it would be undefined. But in this case, if both devices are driving the 1 wire to logic 1, then the wire would be at logic 1. I heard a question. Oh, yes. Yeah, push-pull is describes so what we're describing with that is a driver. So this is the circuitry on a chip that is setting an external pin to a value, to 1 or 0. So those are called drivers. They're basically, now normally when you have a driver, the transistors that are connected to an external pin, an external output pin, are going to be larger than the transistors that are connected to internal signals, because when you go off chip, there's going to be a higher load, a capacitive and resistive load. So, you're going to have these giant transistors that are responsible for sending signals off chip. But then the question is, how do you structure that circuit? Well, the easiest way to do it is basically to use an inverter, basically a big inverter. And I say big because it has to be big to have to provide some amplification, some drive strength. And so that would be a push-pull driver, because the inverter circuit is like a logic gate. Well, it is a logic gate, but it's either going to take the output pin and basically short it to 0, to ground, or to short it to the power supply VDD to set it to 0 or 1. And that's the kind of the most straightforward way to do it. The problem is that if you have multiple chips that have an output that are connected to that same wire, like you have in a multi-slave SPI, then you have an issue if one of those inverters or one of those drivers, push-pull drivers, if one of them tries to pull up to 1 and the other pulls down to 0, you end up with basically an undefined value, and you end up with a kind of a low impedance path from VDD to ground. So you'll end up pulling current out of one chip and then sinking that current into another chip with relatively low impedance, although you have to go through the transistor, and then you have to go through the package, the chip package, and then you have to go through the trace on the circuit board, and then you have to go in the other chip, and then you have to go down through the pull down transistor. And so there is some impedance there, but you're going to end up sinking more current than you should be in that type of logic. So, and more importantly, the voltage of that line would probably be in the forbidden zone. So if you've got like a 5-volt system, for instance, it's going to probably be around 2.5 volts, somewhere in the middle. And it's called the forbidden zone because that value, that voltage, is not associated with a 0 or a 1. So that's the problem. And so that's a push-pull driver. And like I said, if you have a push-pull driver and you've got 2 drivers that are both pulling high or both pulling low, that's not a problem. But the problem is when they conflict, if one pulls high and the other pulls low. Okay. Let's see. Okay, so now question 5 talks about an open drain driver, and that's a little bit different. Instead of using an inverter, it uses well, actually, an open drain driver is an inverter, but it's an inverter using NMOS logic as opposed to CMOS logic. In fact, they used to design, back in the 70s, they used to design whole chips with NMOS logic. But the idea with that is that you have a pull-up resistor and a pull-down transistor. And the advantage with that is if you have two chips connected to one wire with a open drain driver and they have a conflict, one tries to set it to logic 1 and the other tries to set it to logic 0. In that case, it's not bad in the sense that the wire will still have a defined logic value associated to it. Now, you still may have a problem. I mean, you still have 2 chips fighting over one wire, basically. So it's not like there's not an issue at all. You still have a conflict. But the issue, the nice thing about using an open drain driver is that if you have a conflict, the wire still has a logical value, and then you can have the chips kind of work it out, resolve their conflict between each other. And that's kind of the idea between an open drain. So open drain drivers, if no one's driving, it's a 1. If someone's driving it, to 0, then it's a 0. So by default, it's a 1. If you try to set it to 1 on one chip, which means it wouldn't be doing anything, and set it to 0 with another chip, which means it'd be pulling it down, then the chip that that's supposedly setting it to 1 is going to see that it's not 1. It's going to see that it's a 0. Of course, the assumption there is that there's some kind of feedback, into an input, so that the chip is both using that as an input and an output, that pin. And then it would say, oh, I'm trying to send a 1, and yet I see a 0, so there must be a conflict. And that's kind of the idea. So question 5 says, what's the result of one device driving a wire to logic 0 and another device driving the same wire to logic 1 using an open drain driver? Well, in that case, the wire's logic value will be logic 0, and whatever chip is trying to drive it to logic 1 is the loser, basically. So that's, because it doesn't get what it wants. So that's how an open drain driver works. What's the start signal of I squared C? Well, remember that the key to this one is remembering that during a transaction, you don't change the data when the clock is high. If you do change the data when the clock is high, it means that you're doing a start or a stop. So in this case, if you drive the data or SDA low while the clock is high, then that would be a start. And another way to remember that is that, you know, when there's no transactions happening, both of those signals are high because they're open drain. I squared C is an open drain interface. So when nothing's going on, the default state of those wires is 1, 1. And so when you start a transaction, you drive SDA low while SCL is still high, and that's a start. And likewise, question 7 says, what's the stop signal? Is when you drive SDA high while SCI is high. SCL is high, sorry. So now you might say, wait a second, how did SCL get high in the first place? Well, I mean, you have to put SCL high first, and then you drive SDA high. So, but the actual signal that signifies a stop is when the act of changing SDI high, changing it from, you know, changing it at all, changing it from low to high when the clock is high. So in other words, remember that, just remember that when you're sending bits across the channel, you only change the data when the clock is low, right? If you change the data when the clock is high, then that's, you know, a start or a stop. How many times does control of SDA change during a single byte I2C read operation? Okay, so this one is you're doing a read, which means that you send the master sends the address, then you change control for the acknowledgement. So that's one time. And then since you're doing a read, you have to change control again. So no, actually, sorry, you don't change the control. You're doing a read, so the slave will retain control of SDA after the acknowledgement to send the data back, and then you only have to switch control again once more for the master to acknowledge the data sent back from the slave. So the answer is 2 times because you start out with the master in control, then the slave takes control to both acknowledge the address and to send the data, and then the master takes control again in order to send its acknowledgement of the data. So the answer there is 2 times. Question 9 is how many times is SDA, how many times is control of SDA changed during a single byte I2C write operation? And in this case, the master starts out with control. The slave acknowledges the address, then the master takes over again and sends the data, and then the slave takes control again to send the acknowledgement. So you have a change of control for the acknowledgement, the address acknowledgement, a change of control for the data, and then a change of control for the acknowledgement of the data. So that's 3 times. Question 10, what's happening during the following I2C transaction? Okay, so how do you handle this? I think one way to do it is to first start out and ask, like, is this a read or a write? So in order to figure that out, you have to go to the read and write bit. And the read and write bit should be the 9th bit sent. So to find the 9th bit, I'm just going to look for remember that in I2C, the bits are sent when the clock is high. So you just look at when the clock is high and you count 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9th time the clock is high, the corresponding data is 0. And what does 0 mean? 0 means it's a write. You just have to, either memorize that or have that information handy, because it's, obviously that whether 0 is a write or 1 is a write, or 0 is a write or 1's a write, and that's kind of arbitrary. But I2C 0 is a write, so this is a write. So that immediately eliminates the A and B options here, and then so this must be a write, and then the question is, what are you writing, and to where? I heard a question. Oh, sorry. Yes. Sorry. 8th bit. Yes. Sorry. 8th bit. 9th bit is the acknowledge. Thank you. Thank you. That's right. It's the 8th bit. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So luckily, the 8th bit is still 0 data. The data. So thank you. Yeah. The 9th bit is the acknowledgement. Sorry, I screwed that up. 8th bit. So there's a 7-bit address followed by the read-write flag. Okay. So this is a write, and the question is, The value is 3A in both cases, so we're looking for is the address. The option here is choices are 4F or 9E. So now this is a little tricky because it's most significant to least significant. But you know, there's something wrong here with 9E because 9E can't fit in 7 bits. 9E couldn't possibly be an address. That can't be an I2C address because it would take 8 bits to send that address, and we only have 7 because the 8th bit is the read write. So it must be 4F. So you don't even have to look at the timing diagram for that. How can a collision between 2 I2C hosts be detected? Yeah, I don't know if this is actually how it works, but this is just the idea is what would be a possible way. One way is to drive the SDA low. So basically, the idea is that with both the start and the stop bits with I2C, you have to do basically 2 steps. You change one signal, then you change the other. So in this case, what I'm proposing is that you change the first signal. So the first signal you change is SDA, then you change SCL, right? So that's how you start out when you initiate an I2C. Now, I think the way I had it worded before was that if you drop SDA when SCL is high, then that is the start. I never, so is the second part of the start? Well, no, but you know that anyone that's initiating an I2C from an idle channel is going to have to do both things eventually, right? They're going to have to drop SDA then SCL. So if you dropped SDA and then you checked and see if SCL was driven low by another device, then that means that you and somebody else both drove SDA low at the same time, but then the other guy beat you to setting SCL low, right? So obviously that would mean someone else is trying to drive SCL or is trying to start. Now, what happens if you both happen to drop the SCL line at the same time? Well, then that's a problem. But this is just a way that you can, kind of do half of the start and then check and make sure that no one else is doing the second half. Okay, on an I2C read operation, which side drives SCL? Well, the master always drives SCL, so that's an easy one. What's the limitation for adding additional devices? This one is all of the above. There's a limited number of addresses. There's leakage current. Now, to be fair, though, I think I mentioned this, but there's leakage current even with push-pull drivers. The more push-pull drivers you add, the more leakage current you're going to have as well. I think push-pull, though, has a little bit more leakage current as you scale up. And then the collision rate will increase because you got more devices potentially initiating transactions. So those are all true. Master sees a 1-bit during the acknowledgement slot of the data phase. Okay, somebody asked me about this over email. So this question is worded a little vaguely. What I was trying to do with this was I was trying to trick you a little bit. A master sees a 1-bit. Obviously, 1-bit during the acknowledgement slot is a NAC, means not acknowledged. But notice I say during the data phase. This implies that the first part, the address phase, right? It implies the address phase was successful. Because if you get a NAC during the address phase, you're going to abort. You're not going to follow through. Now, I didn't state that in the question, but I tried to imply it, right? So the idea here is that the address phase was fine, but the data phase there was a problem. So so the answer here is the right address was received, but the right data was not received because it was not acknowledged. But the address must have been acknowledged, otherwise we wouldn't be here. Okay, so how many bit slots comprise a single byte I2C transaction? Well, remember we just got done talking about this. There's 7 address, 1 read-write flag, and 1 acknowledge, and that's during the address phase. So that's 9. And then Data phase also has 9 because there's no flag, but there's 8 bits of data plus the acknowledge. So 9 plus 9 is 18. What does a 1-bit signify in the read-write slot? That's a read. You just have to, like I said, you just have to kind of know that. What does JTAG and SPI have in common? Yeah, they require 4 wires. They can be a shift register. They're synchronous, so they're very similar. The difference, by the way, though, there is an important difference with JTAG and SPI, and the difference is in the way in which JTAG sends addresses and retrieves data. It's much different, right? JTAG uses a 16-state machine to and uses an additional signal to set up the endpoints to be receiving an address or a data. So JTAG is much different, sort of in the way that you do reads and writes. Which of these are full duplex? I2C, UART. No, it's SPI and UART. Because I2C is not full duplex. So we had I2C in 3 of the answers. That's why. The 4th one, the only one where I2C is not in the answer, is the right one. In an I2C channel, what's the value of SCL when there's no transactions? Would be 1 because it's the push-pull. And what's the result of one device driving a wire to logic 0 and another driving the same wire to logic 1 in a push-pull? That would be an undefined. Okay, so that's the quiz. Like I said, it seems like just about everyone did really well on that, so that's great. I'm really happy about that. The exam will have very similar questions, so if you're comfortable with this material, then you should be in good shape for the exam. The quiz 3 is on control theory, so let's get back into that. Stop sharing that. Start sharing this. Perfect. Okay, so you should be seeing my slides. If not, let me know. So last time, I think we got all the way to physical system modeling. So just to review a little bit, real briefly, we talked about linear time invariant systems. These are linear differential equations. So basically the idea is that they're time invariant. And so these are linear equations where the variables are actually signals that are functions of time. But because they're time invariant, we don't have to really deal with that time, the time. And in fact, none of the coefficients are dependent on time. So we basically take these signals and we can take the derivatives and integrals of them and multiply them by coefficients and just add them up. So it's linear in that sense, and time invariant in that the nothing depends on the time here in terms of the coefficients in the equation. Yeah, and they're linear in that the reason it's linear is because you can't multiply 2 signals together or a signal by itself. Basically, you can't have a signal squared or multiply 2 signals. That's not allowed. So we talked also about stability, and so an LTI can be stable or unstable. The definition of stability is that if a system defined by an LTI is stable, it means that we will always get a bounded output as long as we give it a bounded input. Any bounded input should give us a bounded output. Now this is kind of complicated because you can build a system that is stable for some frequencies and not for others. But if that were the case, it would not qualify as a stable system because it has to be stable. It has to be bounded for all inputs that are bounded. Now, what does that mean? I mean specifically, well, it means that it doesn't go to infinity, basically, as an unstable system would. And so I mentioned that the goal of control theory, really, the objective of a control theory of a controller, of a control engineer, is to bring stability to an unstable system. But it's a little bit more than that, because usually you also are wanting the system to operate at a set point as well. So it's a little bit more than just making it stable. You want to make the system operate at a desired set point. So I mentioned that, like the plant, like, so for example, an F-16 fighter, the control surfaces are themselves are unstable by themselves. So, if you just had the controls connected directly to the control surfaces, it would be an unstable airplane. But there's a controller in there that stabilizes it. So the controller is constantly making adjustments. So how do you know if a system is stable? There's several ways. You can hit it with an impulse response. The nice thing about impulse response is that an LTI system, if you convert it to the S domain, is already the impulse response. It's free. All you have to do is basically do the inverse Laplace transform, and that's it. That's the impulse response. So by definition, all of these transfer functions that we look at are already an impulse response form, because the S domain version of the impulse is 1. It's a constant. It doesn't have an S in it. Now, if you want to do something like a step response or a ramp response or a sinusoid response, then it's a little bit more complicated to figure out what the response to that is. The way I do it is I just simulate it in software. There's probably a way you could work it out on paper, but I'm not sure. Like I said, I'm not even sure how to do that. I think generally speaking, you just run it through a simulator, which is all the results that I have in the slides here are actually from a simulator. But the impulse response is something that you could work out on paper, and that's the only thing I expect you to be able to do is to work out the impulse response. Also, you can find the poles. Now this part is pretty cool because the poles are basically the values of S that will make the transfer function infinite, or make it divide by 0, basically. The poles, now I mentioned S, of course, is a complex variable. So when you assign anything to an S, the value of S, then it's complex. But if the poles are values where the real component is less than 0, that means that all of the poles are in the left-hand plane. Sometimes I stumble a little bit when I say this, but left-hand plane means that the poles are to the left of the zero vertical axis. So if all the poles are in the left-hand plane, then the system is stable. If any poles are on 0 or to the right, have real values that are positive or 0, then it's unstable. Now, this is interesting, though. Think about this for a minute, though, right? So what does this mean? Okay, if your goal is to design a controller that stabilizes a system, a plant, plant is the thing you're controlling, then all you're really doing is taking the poles and moving them into the left half of the pole 0 plot, right? That's all you're doing. And in fact, that is all you need to do. Is it that simple? Well, yeah, it is that simple, except that all you're doing by doing that is making the system stable. It doesn't necessarily mean you've got a good controller, because you can move the poles over to the left-hand side and you may end up with a controller that isn't feasible to build, because it may put out a control signal that is outside the range of what the plant can handle. It might put the plant into the nonlinear region. Like, for example, if you have a drone, it may try to spin the propellers faster than they'll go. Also, it may be very inefficient. You may want to, say, control the system in a way that minimizes energy. Like you want to save your battery. Like you want a drone You want to control it, you want to stabilize it, but you want to do it in a way that makes it very energy efficient, right? And so that there's a lot of subtleties. Now, this is all outside the scope of this class, but there are controller designs that allow you to not only get the poles in the left-hand side, but do it in a way that satisfies certain objectives, other objectives, like minimizing things or keeping the control output within a certain range. And those are outside I'm not going to cover any of that. And generally speaking, by the way, just so you know, when you do that kind of controller design, you're usually in state space, not in the S space. So there's the S space, the S domain, and then you can also represent these LTIs and controllers in the state space, which is a little bit of a variation. You can convert, by the way, between S space and state space. But anyway, but all you need to know for the purpose of this class is that we want to stabilize by getting the poles in the left-hand side of the pole zero plot. Okay, and then I mentioned you can simulate. Simulating is a little risky though, because like I said, you might simulate it and it might look stable, but that doesn't necessarily mean it is. Okay, so the impulse, the Dirac delta is the impulse. It's basically an infinitely narrow pulse, usually at time 0. And then there's a step function, which is it has the step function is when you take the impulse and you do a integral of the step function, which of course in the S domain is you multiply it by 1 over S in the S domain. So those are two different possible inputs. So here is I think I got to this last time. This is did I cover? Hold on one second. Oh yeah. So let me skip ahead a minute to transfer functions. So yeah, I presented this a little bit in a weird order. So I'm going to skip ahead. So what's a transfer function? A transfer function is a way to represent a plant or a controller. Basically, it's you can put in a block diagram. And in a block diagram, it would be a block, and so you'd have an input and an output signal, and they can be time domain or but generally speaking, you do this in the S domain, and so the transfer function would be when you take the Laplace expression for the LTI, and you just put it into a form using algebra, where one side of the equation is the output signal and it's divided by the input signal. Okay, so you have the output divided by input. So like, for example, like over here I've got Y, and this is the input is U and the output is Y. The block is labeled Y, but the transfer function would be of the form Y of S over U of S, right? And likewise, this is G of S over Y of S, because then if I want to put these two guys together and represent them as a unified system, all I have to do is multiply Y of S over U of S times G of S over Y of S, and that gives me G of S over U of S. So it's basically just, the Y's cancel out. It just becomes algebra, essentially. And then you do this multiply. Now you're multiplying polynomials or ratios of polynomials, but you end up with a transfer function. Now, so all the transfer functions are of this form. That's why it's nice. It's convenient to use the S domain here. Okay, so I'm going to go back again, and yeah. So in this case, I have Y of S over U of S, and this is a transfer function. And normally, the transfer functions, as I mentioned, is a ratio of two polynomials. The polynomials, though, should be a proper polynomial form where they have powers of S, from whatever the order is of the polynomial, and then down to power 0, right? S to the 0th, right? So you don't want any negative powers of S, essentially. And if you do, you can fix that. You can just do some algebra. So in this case, I've got 1 over 1 plus s minus 6s to the minus first power. I don't want that s to the minus first power. So I could just multiply this guy by s over s. So that'll put an s in the numerator. It'll increase the powers of s in the denominator. And then, so that'll give me s plus s squared minus 6. And then I'm going to rearrange these guys to put them in the right order, so which is s squared plus s minus 6. And then in order to find the poles, I'm going to factor the denominator just because that's I want to find the roots of the denominator to find the poles. And so the poles there are -3 and +2. You can label those with x's on your pole 0 plot. Now you might say, wait a minute, are all your poles going to just have a 0 imaginary component? Yes. Yeah, in this class they will. We're not going to do any poles that have an imaginary component. So the poles is -3 and 2. You expect this to be unstable because of the 2. And so to do the impulse response, and this is something, this is the only thing that in terms of doing the manual responses that I'll expect you to do is to be able to basically take the transfer function and decompose the transfer function in a way that allows you to obtain the eigenfunctions. And the eigenfunctions are when you're looking for terms that are in the form 1 over, or any constant rather, over s minus a. And that, because that, when you do the inverse Laplace transform, is e to the at power. And so basically all this, that sounds complicated, but really all I'm saying is let's do some algebra in order to split this denominator into, into its parts, s plus 3 and s minus 2, because I don't know how else to do a inverse Laplace transform when you have like on a polynomial. You have to get it into the proper form essentially. So I mentioned last time that you can do this by basically saying you want a over s plus 3 plus b over s minus 2, because that will be the split, and you want to solve for a and b. So that'll be the split, that'll be the decomposed transfer function. And so you can assume this is what you want, and if that's what you had, then you could go back and recombine them by saying a times s minus 2 plus b times s plus 3. If you did that, you would have a common denominator, which was the original common denominator. You're like, wait a second, that was what you started with, s plus 3 times s minus 2. Then you split it, now you're back. Yeah, well, I did that because I want to solve for a and b, because if I can solve for a and b, and just to be clear, the reason I did that was because by doing that, I now have the same denominator on both sides of this equation, and so I can then kind of cancel that out. So I get s equals a times s minus 2 plus b times s plus 3. Now keep in mind though that this doesn't always work, because if you have repeated roots, this doesn't work out, but this works out because we have 2 different roots. And so again, I'm just going to expect you to be able to do the case where you have different roots. There's another approach you have to use. It's more complex if you have repeated roots. So we have 2 different roots. Obviously, it's 2 and minus 3, and then so I set s to 2 and minus 3, and then I can solve for a and b, which ends up being 3/5 and 2/5. I think I had a bug in the slide last week. I fixed that. And so once you do that, then you can do the inverse Laplace transform. So basically, you take each of these pieces and you match it up to the table. And so so you convert each of these pieces to e to the at, where a is the constant in the denominator, and of course the numerator you can just move out to the front. So this ends up being 0.6 times e to the negative 3t and 0.4 times e to the negative 2t. These are the eigenfunctions. And because these are in time domain, you can just vary t and plot this. You can plot the value of the function versus time. And this now, it's a little weird though, because see, what you're not seeing here is the input. The input is the pulse, is the Dirichlet delta, right? So you generate the plot for this, and you see that when you plot it, it's not bounded. The value just goes to infinity as we increase time. But you have to understand that what you're seeing is the impulse response, which seems crazy because you never actually hit it with the impulse. You just you did this eigenfunction transformation and you just varied, you increased time and you got the impulse response. You can also do a step response, and which I don't know how to do by hand, but I did it in MATLAB, and so so step response is just basically where you go from 0, you step it up to 1. Now, both the impulse response and the step response contain all frequencies. It requires an infinite number of frequencies to add together to get either one of the step or impulse response, because you have to add an infinite number of frequencies, sinusoid frequencies, together to get this kind of this step shape, right? And so that way, this is why this is a good test for stability, because this is going to basically feed the function every frequency at once. Now, when I do the step response, when I do the impulse, you see it just goes zip, it just flies straight up. But when you do the step response, you get this crazy ringing that increases in magnitude infinitely, which is kind of crazy to see that. It just starts waving at first it's real subtle, and then it gets bigger and bigger and bigger and bigger. So I think that's pretty funny how that works out. And then of course you can hit it with a single frequency. This is risky because technically it's possible to give it one frequency and it not go to infinity. But in this case, I just gave it I gave it 2 radians per second because in fact that was one of the poles. But I tried to give it a couple other ones, and I was still getting it was still blowing up on me. So I wasn't actually no matter what input I gave this function, it diverged to infinity. Anyway, so let's look at another one. I just changed it I changed the denominator in here in this transfer function to s+3 times s+2. That way I have 2 negative poles. This puts the poles in the left-hand side. And then I worked through the same math, and I got A is 3, B is -2. And so I got slightly different eigenfunctions here, which, they don't look that different, but boy, you get a much different impulse response. Now this one I had a bug. I think this was the slide I had the bug in actually last week, and the shape of the plot was a little different, but it was still stable. So this one is kind of crazy. Look, it goes down, it goes a little bit negative, starts at 1, goes negative, then goes up, and it kind of converges on 0. I think that's pretty cool. And then likewise, I did the step response. The step response, once again, is much different from the impulse response, but it still converges on 0. And then the sinusoidal response is pretty much just the same as the input signal. I don't even get a phase shift here, but I do get an amplitude difference. So the amplitude of the input is 1, the amplitude of the output is 0.2. I don't really care. It's just the point is that it's stable. Okay, so I mentioned transfer functions. So transfer function is basically just, it's an LTI S domain put in the proper form, output over input. So these transfer functions are usually just, ratio of 2 polynomials, generally speaking. The denominator polynomial, though, is generally shown with a 1 coefficient on the highest power of S. But again, it's not necessary. You can always adjust it algebraically. Okay, so then I think last time I just started talking about physical system modeling. So this part is, this gets really complicated. The point of this is that I wanted to show you how you go about modeling a plant. Now, I can't go, I'm not going to go too much into this because this is really more of a, this starts to get into physics or, like electrical engineering type thing. Obviously, we're interested in modeling systems that are RLC circuits, analog circuits. That's a big one. So I mentioned like in power electronics, that's what you're doing. Any kind of pendulum sort of system or any type of motor-based system works well here as a, modeling as an LTI. And that's kind of, in flight controls, avionics, those are, in vibrations too. Like if you have a cantilever beam that's vibrating, you can model its vibration using the stiffness and the mass. But those are, doing all that is kind of like, physics stuff. So I'm going to just show you a really simple one where this is literally just, I have an object and I want to push it to a specific position. That's it. Which seems kind of trivial, but you have to take into account that we're going to give the system an input, which is going to be a force. So this is part of part of this is part of the challenge here is keep in mind that you have two signals that you're interested in. There's an input and there's an output. So when the input is U and the output is Y. Y is the position, U is the force. But the way I have the system represented, you have to make sure that all of the terms in your transfer function have the same units. So the units here is going to be newtons. This is all force. So all of the terms are going to be in terms of force. Well, U is already going to be a force, right? But Y is a position. That's not force. So in order to convert the position into a force, I'm going to do mass times acceleration. So I'm going to take the mass of the object and multiply it by the second derivative of y, which is the acceleration. So the my dot dot is a force, and u is a force. And then you have friction, which is b times the velocity of y. And so it turns out that when you calculate friction, and you guys probably know this better than I do, having taken physics recently, but the friction here is a force that's working against u, which is my input force, and it's calculated as a b times the velocity. So the faster something moves, the more the friction fights back against you, essentially. So the friction is a function of velocity, so it's b times y dot, and that still gives me a force. So all three terms in here are a force. Now, you can imagine that you don't always do it that way, though. Like you could have any units involved. As long as everything agrees on a specific unit, it doesn't have to have force. In fact, in the quiz, I came up with another one for you. I came up with an example in the quiz that is a pendulum. And in the pendulum case, we're interested in theta, which is the angle of the pendulum. Basically, the idea of that is I wanted to come up with a neat, like the idea was to have a cyber-physical system that will automatically push your daughter on a swing, like so at a set point where the maximum theta is the set point. So you want to keep pushing, you want to apply a force, but you want the swing to always, swing at the same, angle. It's kind of the idea, which would be a pretty cool device, I think. But so that in that case, the unit was, was the angle and not the force. So in that case, if you have a force that you're putting in, then you have to, convert it back to an angle. It's kind of the idea. So anyway, so in this case, U is the input force. The friction fights back, so I subtract that, and then the difference of the input and the friction is basically the output, which is the actual force. But ultimately, Y is the signal I'm interested in. so y is the output, that's the position. So my goal is to try to move, the set point is y, is a certain y. I want to take the device, or the object. I want to push an object at a given y at a given location. I don't want to push it too hard. I don't want to push it too, well, I could push it too slow because, but if I overshoot the destination, then of course I have to apply a negative force and push it back. So hopefully, I can do that. Now, this by itself is an unstable system because, you know, if you apply a constant force, then, you know, it blows up to infinity. You just keep pushing endlessly, right? So, so anyway, so what's the challenge here? Well, the challenge is, one, to write the equation, and two, to transform it into a transfer function. Well, how do you do that? Well, you know, you do the Laplace transform, which is easy. So y dot is the shorthand for dy dt, so that becomes you know, s, and y dot dot is d squared y over dt squared, the double derivative, so that would be s, that would be Laplaced into s squared. And then I need to get into the proper form, so I just have to move things around. I need to get y over u, so I'll get my u's on one side and my y's on the other side, which is easy because I just have one u. And then I divide the y out, and so I end up with mass times s squared plus bs in parentheses multiplied by y, and then I can divide both sides of the equation by y, but that will actually give me the wrong transfer function. That will give me u as a u is the output and y is the input, and I want them to be the reverse. So I just basically take the reciprocal of both sides, and I get y over u over 1 over ms squared plus bs. And so that polynomial form, ms squared plus bs, is my denominator. And so you can see, if I factor out s, of course, you can see that one of the roots, of course, would be 0. The other root, sorry, not root, pole, one of the poles would be at 0 because of the roots of that denominator. So one of the poles would be 0, and the other pole would be negative b over m. Of course, b and m are, you know, dependent on, you know, the friction and the mass of the object, but they're just constants in this case. So yeah, so it's unstable. Yeah, sorry. That was okay. So then here's the step response. You know, predictably, you know, this would be like saying, okay, 0 force until time 1 second, and then at 1 second, I'm going to apply a constant 1 Newton force forever. And of course, you know, as you might imagine, you just push it forever. So to control something like this, we need a closed loop control, and the closed loop control is when you have the plant, and it will be fed by the controller, and these two guys together represent a system. You just multiply them together, and you get a single transfer function representing both, and that is actually the open loop controller. So if you're only doing an open loop control, you're done. If you're doing a closed loop control, you have to add a feedback, and the feedback is the output of the plant fed back and subtracted from a set point that you want. Now, if you had an open loop controller, your set point would go straight into the controller. But like I said, without the feedback, your system can't deal with uncertainties and disturbances. So that doesn't mean that people don't use open loop control. It's used a lot. But closed loop control is common, you know, when you have this potential for, you know, disturbances. Now, in the case of, you know, you might think, wait a second, if this was like an RLC circuit, you know, capacitors and inductors and resistors, they always work the same way. I mean, why, you know, would you need a closed loop control? Yeah, because there's, you know, there's you know, manufacturing variations, and also if you're doing power electronics, it turns out that the cool thing about power electronics, and you might not be interested in this because it's more electrical engineering, but in power electronics, if you're designing a converter like a DC-DC converter, the problem with that is that the load, your control has to keep the voltage, the output voltage, stable when you're changing the load. And so what happens, like with an electric vehicle, your goal is that, you know, when you hit the accelerator, for instance, you know, you're changing the load on the DC load, and you need to be able to very quickly adjust the controller for the DC-DC converter to maintain a constant voltage despite the load changing. So anyway, that's kind of the story about that. Okay, so yeah, so the goal here is to calculate the transfer function of the closed loop control. So I already mentioned to you that the open loop control we've already done. It's just GC times GP. That's the open loop transfer function. We're done. That's all you have to do. The closed loop is a little bit more complex though. So basically, you have a third object in here, right? You have this differencing thing. So basically, the closed loop control is the open loop control, which is GP times GC, multiplied by RREF minus the closed loop transfer function. And that's it, except you know, we want to get the YCL. We have to do some algebra here to get YCL, isolate that on one side. So to do that, you basically just multiply this out. So you have GP times GC times RF minus GP times GC minus times YCL, sorry. And then you take the terms that have YCL and you move those to the left. So you take this guy minus GP, GC, YCL, and you add it to both sides of the equation. And then you factor out YCL, and then you divide both sides by 1 plus GP times GC. So yeah, that's basically it. You know, pretty simple, just some algebra, right? Except that the real transfer function of the whole system is, you know, if you think of this as a total control system, you want to know what the response of the YCL is relative to the reference, which is the overall input. So in that way, you can consider that the reference. So basically what you want to know is you want to divide, you want to know what YCL over RREF is. So all you have to do there is divide both sides of the equation by RREF. So all that does is take out the RREF from the right-hand side and put it as a denominator under the left-hand side. So you'll have YCL over RREF, which gives you the transfer function of the closed loop. So this thing is how you arrive at that. This is a very common, this is basically the known as the closed loop transfer function. It's just the open loop divided by 1 plus open loop. That's it. That's how you, that is the you know, kind of the canonical closed loop transfer function form. What I've done here is just show you how it's derived from, you know, just multiplying these guys out. Now you can come up with, you can have, like, say, you might have 3 blocks in here in the open loop. Like you might have GC and then something else and then GP. Or you could have this nested in various ways. Like you could have a whole closed loop system inside of this open loop thing. Like you could have a closed loop thing nested inside here. Now you might say, well, why would you have that? Well, that's actually very common. For instance, you might have, like, if this is a drone, you will have a separate controller inside of a drone that just controls the rotors, that just like basically, you know, you send an input into the rotor and you want the rotors to spin up and you want them to stop spinning up once it hits that set point, right? But then you're going to take that closed loop thing and you're going to enclose it into a bigger closed loop system in order for the drone to maintain a certain altitude, for instance. So this transfer function is something that is nestable. You know, like basically all you can compose arbitrarily complex systems by just, you know, applying this closed loop equation, and you can, you know, you can take like a whole closed loop system and put it as the open loop inside this outer, you know, closed loop thing. Okay, so what about the controller? We haven't really talked about the controller. How do you build a controller? We talked about how the plant is realized, is modeled, but how is the controller model? How do we build the controller? Well, that is there's many ways to build controllers, actually. One way to do it is the PID controller. This is one that you guys, I think, are already familiar with from CSCE 274. I'm not sure how formally they presented the PID controller. The PID controller is pretty simple, though. It's basically the idea is that you take the error term, which is the difference between the output of the plant and the reference, and you multiply that by a proportional control, and that gives you the proportional output. And then there's a derivative where you look at the derivative of the error and multiply that against the derivative control. And when I say control, I mean these are constants that you set when you're tuning the controller. And then there's also a integral control, which is you take the integral of the error and you multiply that against the integral term. So you end up with like three constants: kp, kd, ki. And so the proportional control is used to you look at how far away you are from where you want to be, and and you multiply that against the proportional term, and you apply that to the input for the plant. The derivative is used basically to slow down once you get closer, and then the integral is to cut down on the ringing that you get. You could model these as three separate controllers, or you can put them all into one transfer function. So if you put them all into one transfer function, it would look like this in the time domain. So it would be GT equals GP times the error. Oh, hold on a second. That's time domain, so that should be lowercase. Sorry. Lowercase e, lowercase e, lowercase e. Yes, sorry. So in the time domain, use lowercase. Lowercase function names, everything's in the T. The time domain, and then if you go to the Laplace, then you just go to S domain, and everything becomes capitalized. Now, in this case, I've used some shorthand. Because normally E of T or E of S would be over here, but I've used some shorthand. I just assume that we've already factored out the E of S and put it in the denominator on the left-hand side. Probably shouldn't have done that, though. I should make it more. I should be more formal about that. And then, of course, once you do that, you end up with, of course, the integral is the Laplace of the integral is going to give you 1 over s. That's s to the minus 1. So I'll multiply both sides of this by s over s to get to put the numerator as a proper derivative. So now notice that the PID controller ends up being another ratio of polynomials of s, which is what you generally will see with these transfer functions. But notice that the controller has a second order polynomial in the numerator and a first order in the denominator, which is a little different, but yeah, it's valid. And then, of course, you can also do a PI controller that just eliminates the derivative part, which I did just to simplify this, because I tried to work out an example with the full PID, and it just became too cumbersome. So we'll just do PI. And as it turns out, also, we don't. It seems to work fine with this plant to not have the derivative part. So this is the proportional and integral parts. And I'm going through this kind of fast because I'm assuming you guys are pretty comfortable with this from robotics. Okay, so let's look at an example. So let's take the plant, which is 1 over m over s times s plus b over m. That was the transfer function of the plant. That was basically, moving an object to a line, or just moving an object in general and giving a y output where the input is force. And then I've got my PID controller, which I multiply against that to get my open loop transfer function. So far, I'm just working on the open loop transfer function. That's GC times GP. And so I multiply those together, and I'm just going to simplify this by setting the mass to 1 and the coefficient of friction to 1, just to simplify this a bit. So now I end up with just 1 over s times s plus 1 for my plant. And then my controller, I'm going to leave the kp and ki as variables, because once I figure this stuff out, I'm going to have to set those to tune the controller. So, so my closed loop transfer function, after I multiply these guys out, and I'm going to kind of blast through this kind of quickly here, but basically, you know, this is just 1 times the kps plus ki, and then the denominator becomes s squared times s plus 1. So now I have, that's my open loop transfer function right there. And so now I have to substitute it into my closed loop transfer function, which is the open loop over 1 plus the closed loop, right? So now you can see this is where it kind of got too crazy when I had the derivative term in there. So basically, I need to work all this out, and I mean, I need to get this into a form where it's polynomial divided by polynomial, right? So hold on 1 second. Okay, sorry, I had to close the door. Okay, so so basically, it's just time to do some algebra. So so I took the denominator and I merged it into you know, 1 ratio, one fraction. So that 1 became the denominator. So s squared times s plus 1 plus kps plus ki divided by the common denominator. And once I got the common denominator, then I was able to cancel that out. So now I have kps plus ki over the numerator that I had on the fraction, on the bottom there, which was s squared times s plus 1 plus kps plus ki. And so just rearrange that a little bit, multiply this guy out. So now it's s cubed plus s squared plus kps plus ki. So now I have a proper polynomial in the denominator, and now I have a proper polynomial there in the numerator. But what do I do now? Now there's a problem, because I need to determine if this is a stable system, and in order to do that, I have to factor the denominator, find the roots of the denominator, and the denominator is an order 3 polynomial. So I basically said, well, okay, when you have an order 3 polynomial and you factor it, I'm expecting this to be like s plus something times s plus something plus, s plus something times s plus something times s plus something. So I've got these, you know, components a, b, and c in there. And so if I were to take this generic form and, you know, multiply it out, you know, but retaining the a and the b and the c. Right now, just forget about the transfer function. I'm just speaking in general terms right now. This is just in general. So s plus a times s plus b times s plus c is going to be s cubed plus a plus b plus c times s squared plus ab plus ac plus bc s plus abc. So now I need to pick values for kp and ki that, you know, will stabilize the system, right? So all I want to do is I need any value, I don't care if they're, I mean, at this point, I don't care if this is a good controller. I just want something that'll give me that'll stabilize on the set point. So I just kind of did this I kind of wing this, and really there's, you know, when you're dealing with this sort of controller, you know, this is one way to do it, is to basically, I know that a plus b plus c has to equal 1 because the coefficient in front of the s squared term in my polynomial is 1, right? So I know that. So, and then I know that a times b plus a times c plus b plus c, which is how you get the coefficient in front of the s term. That's going to be kp. And then a times b times c is going to give me ki, which is my, you know, the constant, the standalone coefficient in there. So all I need to do is, you know, I'm just going to come up with values of a, b, and c that add up to 1, and then from there I can get kp and ki. And so I just did that. So, okay, a is 0.25, b is 0.25, and c is 0.5. And I literally just came up with those like just off the cuff, you know, just pick 3 values that add up to 1, essentially. There was no strategy whatsoever to this, just any 3 values that add up to 1. And I was curious how this would work out, right? So once I have those, then I can feed those values back in. I can get my proportional and integral control. So my proportional is 0.3125, my integral is 0.0313. And so so I went ahead and plugged those into the control transfer function. Oh, sorry, no, not the control, the whole thing, the open loop or the closed loop transfer function. Sorry, this is the closed loop transfer function. I plugged them back in, and I got the step response. And check it out, it's stable, right? I mean, it should be, right? Because the because you know A, B, and C, you know, they're all positive. So when I take the roots, you know, obviously all of the roots are going to be negative, right? So, you know, I expected it to be stable, but that's the actual impulse response. And you can see that, yeah, it's stable, right? So that's pretty cool. And then I hit it with a step response. Now the step response is actually indicative of what the controller is going to look like when you use it. So this, think of the step response is, I want the object at y equals 0. Now I want the object at y equals 1. And so you change the reference, which is the input, you know, to the whole closed loop transfer function. And in response to that, you're going to see y, which is the position of your, you know, your coin or your marble or whatever you're, you know, dragging across the tabletop. And you're going to, hopefully, you're going to start to see the controller, the y should track the set point, right? Which it does, right? So I go up, but it's kind of crazy because you see it, you know, like you see it go up and then come back down. Now, what you're not seeing, by the way, all you're seeing in this plot is the input, the reference input, and the y. You're not seeing the input from the controller to the system, right? You're not seeing the force being applied to the object I'm moving. All you're seeing is the input and the output. But it's easy to plot that. I do that. I'll have that in the next slide. You can just probe that in MATLAB or whatever software you're using. But notice that before we get to that, notice that the object being moved, there's an overshoot where we exceed the set point and then come back down, and then there's a rise time. Now this is what I was talking about when I was saying that even if you have a controller that stabilizes an unstable plant, it doesn't mean it's a good controller, because it may be more desirable to have a steeper rise time or less of an overshoot, or other things. There's other, you know, there's a whole variety of different sort of criteria that you may want to have when you're designing your controller. But this rise time and overshoot are, I mean, you can see quite clearly these are kind of undesirable. I mean, the rise time is too slow and the overshoot is too high. I mean, you can kind of see that pretty plainly. So, so let's take a look at maybe going back and tweaking a little bit. Now, again, I mean, this is kind of ad hoc. I'm just going to increase I'm going to take the KP and bump it up to 1.25. And you can see that this is the before and the after. And you can see when I increase the proportional response, it made the rise time better, but it didn't do anything about the overshoot. So the overshoot went up to about almost the same level, right? So rise time was better, but now I need to do something about the overshoot. So I'm going to increase the integral part. And look at that. It actually, when I increased the integral Ki, the integral coefficient, it made the overshoot even worse. It went beyond 0.06 there, right? So obviously increasing Ki was the opposite of what I should have done if I was concerned about this overshoot. So, that's just some examples. I don't want to go down, too far into that because this is not a control theory class. And I want to get to the more important thing, which is the discretization of this controller, which is when you actually, what happens when you run this on a computer. But here's another plot. I did this just because I wanted to show you, I went in and I plotted the actual, I put this orange line. The orange line is the input to the plant from the controller. And so you can see that if you superimpose that, this is the actual force that I'm applying to the thing I'm moving. You can see it goes up and then it goes down and then it goes negative because I have to, well, I pushed it too far. I got to pull it back. And that's what the orange line is. And then I thought, well, why not hit it with the sinusoid? So the sinusoid represents, let's say I want to take an object like, just imagine I'm moving a coin across the table. And I want to, my set point is a sinusoid. I want to move it back and forth, And so notice how the y, it works, right? Except notice how the yellow line, which is the position of the actual coin, and the blue line is my set point where I want it to be. Notice how it lags, right? So one of the things that's, happening here is that this controller is kind of slow. I mean, ideally these two traces would be lined up closer to one another. So again, I mean, this is something I can tweak to try to make the controller a little bit more responsive. Okay, all right, so that's all we have for today. So in the next lecture, hopefully I'll be able to finish up the control theory material. I'm going to talk about how to actually implement a controller basically in a C program on a microcontroller, because that's ultimately what we're most concerned about. And I'm also going to talk about sample time, because believe it or not, none of what I've showed you so far is implementable on a digital controller. All of this stuff I've been talking about is in the S domain, and the S domain is the continuous domain. It's not discrete, it's continuous, meaning that all of the controllers I've shown you are basically can only be implemented as an analog system. Now you might say, wait a second, you ran it in MATLAB, and MATLAB is running on a digital computer. Yes, but MATLAB is actually faking it by running these things still in discrete time, but a very small time step. And it's not suitable for like a real-time controller in real life. In other words, it's not real time. It's not doing it in real time. In real life, we have to do it in real time, and then we have to worry about not running it at a super low time step like MATLAB is. So then we have to be concerned about how the time step affects the stability. And then in the next lecture, I'm going to talk about real-time scheduling, which is what the actual how to design a controller that actually does this in real time and enforce real-time performance. So that's all I have for today. If you have any questions, I'm a little bit past time. Sorry, I tend to yap too long. Is everyone still here? That's a good question. Is the class canceled on Monday? Why is it canceled? I forget. Oh, is it a holiday or? I forget why it's canceled. Sorry, you got me with that one. President's Day. Oh, yeah. Okay. Yes, thank you, Charles. Yeah, I guess we'll postpone it then. Either to Tuesday or Wednesday, I guess. Yeah, I'll send an update. I'm sorry. Yeah, you can assume the quiz will be postponed, the due date, but I'm not sure how much yet. I'll send an update. We'll let you know. Thank you. I forgot about President's Day. It's so hard with the with the virtual. Okay, great. All right, that sounds good. If you have any other questions, let us know, and feel free to check out the quiz. It should be open now. If you find any typos or bugs, let me know. I expect there to be some because there was a lot of math I had to put in there, and whenever you do that, Moodle tends to, there's characters you have to escape and stuff. So If you have any bugs, let me know. I'll fix them and send out updates. Thank you, everyone, and we'll see you on Wednesday.